The concept of hyperdimensional computing, HDC, represents one of the most radical departures from traditional computing paradigms in the history of artificial intelligence. At its core, HDC is built on a deceptively simple idea. Instead of processing information using binary bits organized into low-dimensional structures, it uses vectors with thousands of dimensions to represent and process information. This approach is inspired by the way the human brain operates, where information is distributed across millions of neurons, each contributing a small part to the overall representation. The result is a computing framework that is robust, efficient, and remarkably well-suited to the emerging landscape of edge AI and neuromorphic hardware. The mathematical foundation of HDC lies in the properties of high-dimensional spaces. In a space with 10,000 dimensions, random vectors are almost always nearly orthogonal to each other, meaning they are effectively unrelated. This is a consequence of the geometry of high-dimensional spaces, where the volume is concentrated near the surface and the distance between random points is almost always the same. This property allows HDC to represent an enormous number of distinct concepts using random vectors as atomic symbols, with minimal risk of accidental similarity. The operations used in HDC, such as bundling, addition, binding, multiplication or XOR, and permutation, allow these high-dimensional vectors to be combined in ways that create new vectors representing complex relationships. These operations preserve the properties of the high-dimensional space, enabling robust and efficient processing. HDC has been proposed as an abstraction layer that enables the design of algorithms for emerging hardware platforms that operate with massive parallelism, ultra-low voltage, and unreliable components. The robustness to noise and inherent randomness of HDC makes it particularly suitable for these stochastic execution environments. This is a crucial advantage because traditional computing architectures are reaching their physical limits, and new approaches like in-memory computing and neuromorphic processors are needed to continue the trend of increasing computational power while reducing energy consumption. HDC provides a bridge between application design and these new hardware platforms, allowing algorithms to be described in a way that is both expressive and efficiently executable on the underlying hardware. One of the most impressive demonstrations of HDC's potential is in the domain of language identification at the edge. Researchers have developed a hardware algorithm co-design framework that leverages analog in-memory computing and HDC for efficient language identification on edge devices. By exploiting the inherent randomness and multi-state properties of analog memristors, they implemented a vector matrix multiplication-based language feature encoding with greatly reduced hardware complexity. Language classification is then realized with a single-layer perceptron on analog memristive crossbar arrays, eliminating the need for interlayer activation functions and backward propagation during training that are required in deep neural networks. The experimental implementation on a multi-core memristive system on a chip demonstrated a remarkable 90% reduction in hardware resources while achieving 95.24% language identification accuracy, the highest reported among HDC implementations on emerging hardware platforms. This work provides a scalable, energy-efficient approach for high-accuracy language processing on edge devices. The applicability of HDC extends well beyond language identification. A comprehensive survey of the field by IBM Research covers applications in machine learning, cognitive computing, and various other domains. The survey notes that most HDC applications lie within the machine learning and artificial intelligence domain, but the field has also found applications in areas such as robotics, healthcare, and natural language processing. The cognitive processing functions that HDC can support include perception, attention, memory, learning, reasoning, planning, and communication. This makes HDC a promising candidate for a unified approach to artificial intelligence that can be deployed in a distributed manner at the edge, even in environments with contested communications and limited compute and power. The NATO Science and Technology Organization has recognized this potential, identifying VSA/HDC as uniquely able to provide the required algorithmic and data layer for distributed cognitive processing functions on current and future emerging hardware. The efficiency of HDC is not just a theoretical advantage. It has been demonstrated in practical implementations. Optimizations such as in-memory processing and special memory architectures have been applied to improve chip area and throughput. One implementation demonstrated an FPGA implementation that uses deep adder trees to perform inference in a single clock cycle, showcasing the potential for real-time processing. Furthermore, HDC has been studied for its reliability under real radiation conditions, which is critical for safety-critical domains such as autonomous vehicles, medical instruments, avionics, and nuclear power plants. These studies are essential for ensuring that HDC can be deployed in the most demanding environments. A fascinating development in the field of HDC is the exploration of its connection to four-dimensional spatial computing. One approach proposes a 4D Cantor tesseract structure where consciousness is treated as the fourth dimension. This conceptual framework extends 3D Cantor dust with a fourth axis representing metaconsciousness or awareness level. The W dimension encodes different levels of awareness. W equals 0 for unconscious/automatic processing. W equals 0.5 for aware, but not meta-aware, and W equals 1.0 for fully metaconscious. This structure provides a novel way to model cognitive processes in a high-dimensional space, with the potential for a richer representation of information and relationships. Another line of research explores the feasibility of building neural networks able to detect, assess, and quantify a fourth spatial dimension. Starting from two-dimensional shapes embedded in a 2D topological charge pump, it is feasible to achieve corresponding four-dimensional shapes that encompass a larger amount of information. Synthesis of surface shape components, viewed topologically as shape descriptions in the form of feature vectors that vary over time, leads to a 4D view of cerebral activity. This approach permits an increase in the amount of available qubits in a fixed volume, potentially enabling more powerful quantum computing applications. This novel, relatively straightforward architecture could increase the amount of available qubits in a fixed volume, offering a path to more powerful quantum computing. The potential of HDC is further amplified by its integration with quantum computing. Novel quantum machine learning models that combine both quantum and hyperdimensional computing have been introduced. These models have been theoretically demonstrated and applied to prototypical machine learning tasks such as pattern completion, classification, and clustering. The accurate and promising results prove, for the first time, the synergies between two of the most innovative computational approaches, quantum computing and hyperdimensional computing. This integration could address the inherent limitations of HDC on classical hardware, particularly regarding storage capacity for large-scale data and high-complexity tasks. The algorithms used in HDC applications can often be separated into three stages: encoding, training, and inference. The encoding stage is the most important and is application-specific, serving to map objects in the input space to hypervectors in the high-dimensional space. In a learning setting, the training phase aggregates hypervectors into prototypes to learn a model. Inferences can then be made using the generated class representations by comparing their similarity with an encoded test sample. This relatively simple pipeline enables a wide range of applications, from classification and clustering to more complex cognitive tasks. The properties of HDC have also motivated its application to more general computation problems, often referred to as stochastic computation. Research in this domain seeks to create solutions to classical problems such as hashing and graph isomorphism by exploiting the characteristics of HDC. These applications encompass both deterministic computation in the presence of noise and probabilistic algorithms that search for approximate solutions. For example, GraphHD is a graph classification method that uses HDC, and HD hashing is a dynamic hashing algorithm. These applications demonstrate that HDC-based approaches have the potential to bring efficient and robust alternative solutions to relevant problems. The challenges facing HDC are also being actively addressed. The field is working to better understand the theoretical foundations of HDC, to develop more efficient encoding schemes, and to create robust hardware implementations. A comprehensive survey of the field, published in ACM Computing Surveys, covers foundational aspects such as the historical context, key elements of any HDC model, known HDC models, and the transformation of input data into high-dimensional vectors. This foundational work is essential for building a solid understanding of the field and for guiding future research. Hyperdimensional computing represents a paradigm shift in how we approach artificial intelligence and computation. By leveraging the properties of high-dimensional spaces, HDC offers a path to more efficient, robust, and intelligent systems. Its ability to operate on emerging hardware platforms, its resilience to noise, and its cognitive processing capabilities make it uniquely suited for the edge AI applications of the future. As the field continues to mature, we can expect HDC to play an increasingly important role in everything from language processing on smartphones to autonomous vehicles and space exploration. The fourth dimension in artificial intelligence is not just a mathematical abstraction. It is a practical reality that is already being deployed in real-world systems, and it promises to reshape the landscape of computing for decades to come.